So calculus, we are going to continue on with 5.6. It's another application of the derivative, and we're going to do L'Hopital's rule. Some math books add an S into his name. So you might hear students say L'Hospital, but it's pronounced L'Hopital, and I don't even know what that symbol is called. But what he came up with, well, he actually stole it from other mathematicians, but he wrote it in a book, is a rule that makes finding limits a lot easier. And what it boils down to is the indeterminate form that we've talked about from a long time ago, which was 0 over 0, infinity over infinity, and many forms of that. And by the way, there's more forms of L'Hopital, but this is all you need to know for Calc AB, is these forms. So anything that's infinity over infinity or 0 over 0, and it's indeterminate. So as you recall from Unit 1, we did problems like this, and we could. We didn't need to know L'Hopital's rule to do this because we could factor. So if you were to factor the numerator, I guess I should have written out first that if you plugged in 3 into the numerator, you'd end up with 18 minus 3 minus 15. You get 0 there. If you plugged in 3 into the denominator, you'd have 9 minus 3 minus 6, another 0. So that was a clue that we had an indeterminate form and we could factor. So had we done that, let's see, that would be 3 and 5, right? 3 and 5. Let's see, 2x times negative 3. There we go. And then down here you'd have x plus 2 and x minus 3. That way we could factor out these x minus 3's, and now we could plug in 3. So 2 times 3 is 6. 6 plus 5 would give me 11. And 3 plus 2 would give me 6. And that should be our answer. Okay, so what is this? What is L'Hopital's rule? Well, how about this? Let me just give you the answer and show you that piece. Is if I asked you to do L'Hopital's rule, what you would do is once you identify that it's 0 over 0, and you would probably want to write down that L'Hopital's rule. You can even just write down L'Hopital's. What you do is you just do the derivative of the top, which would be 4x minus 1. And then you do the derivative of the bottom, which is 2x minus 1. And then you plug in 3. Well, 4 times 3 is 12, minus 1 is 11. And 2 times, oh, I did this math wrong. I'm glad I double checked it. 3 plus 2 is 5. 2 times 3 is 6, minus 1 is 5. And you get the same answer. So you know me, I'm going to show you the answer key. Now I'm well aware that I did not follow the directions up here, but had I done this correctly I would have gotten 11/5. So here's L'Hopital's rule. If the limit as x approaches c of f of x in the numerator equals 0, and limit as x approaches c of g of x, that's the denominator, is equal to 0 as well, so you have 0 over 0, then you just take the derivative of the top and the derivative of the bottom, and that limit will be equal to, had you originally done the limit as x approaches c of f of x over g of x. And the same thing works if we had infinite limits. The one thing I don't like about this guy's definition is he leaves off that f and g should be differentiable. When I scored over the summer, they actually didn't require students to write out that L'Hopital's rule applies as long as the f and g are differentiable functions. So I think that's why he left it off, is because it's something that is necessary, but they don't take off points for whatever reason. I guess the College Board thinks that this rule is difficult as it is. One more thing to notice is at no point did this author write down equals 0 over 0, because that is not correct. If I won't go back to my notes, I wrote arrows here. So you either need to write out arrows, or, and they allowed this, you could write it out individually. That you could write out because 2 times 3 squared minus 3 minus 15 is equal to 0, and 3 squared minus 3 minus 6 equals 0. Then we can use L'Hopital's rule, which is the derivative of the top and the derivative of the bottom, and then direct substitution. Notice that it is not the quotient rule. I've seen so many students try the quotient rule here. You do not do the quotient rule on this problem. Okay, and I already did that. All right, I think I'm ready to do many, many more examples. So you don't have to write out in these problems that you have differentiable. But I think it's important as a teacher, I should be mentioning it, but on the College Board, on College Board, the AP test, you don't have to write out that sine of x and x are differentiable. But it is true. So I'm just giving you that little notation. So you don't have to, but it is nice. You may remember earlier in the year, we memorized this fact, and we talked about it at pretty great length. Well, what you do have to do is you do have to either write out that sine of 0 is equal to 0, and if you plugged in 0 for x, I know it probably seems like a redundant statement, that 0 equals 0. Or, this is an option 2, you can just put arrows that you get 0 on top and 0 on bottom. But any way you think about it, we have 0 over 0, which is indeterminate. So because it's indeterminate, then we can do L'Hopital's. By the way, this has been on every test for the last 3 years. As soon as they put L'Hopital's on Calc AB, this has only been a few years since they've done this. It's been on every test. So what do? You take the derivative of the top. Well, the derivative of sine is cosine, and the derivative of x is 1, and now you can directly substitute, and cosine of 0 is equal to 1, which is exactly what the direction said it would be. So again, I'm going to leave off that these two functions are differentiable, but they are. You need to either put arrows that say, okay, well, plugging in cosine of 0 would give me 1 minus, and you could write it out, cosine of 0, which equals 1 minus 1, which equals 0. And then down here, you just get 0. So we have 0 over 0, which is indeterminate, which means that we can do L'Hopital's rule. And by the way, I don't care if you put an S in there or not. I don't even care if you put a, they don't count off for spelling, so it doesn't really matter. So if you're doing L'Hopital's, what do? Notice that the limit as x approaches 0, that stays the same. You just do the derivative of the top. Well, the derivative of 1 is 0. The derivative of negative cosine is positive sine. And then the derivative of x is 1. And now when you plug in, now is when you put your equal. Sine of 0 is 0, which is exactly what we learned a long time ago, which feels like a long time ago. And the reason why this is expected for students to know now is we can do very, very difficult problems. I'm sure you are looking at this and saying, man, I would have hated to do this problem ages ago. And I would agree with you. Because if you were to look at pi over 2, that's the order pair 0, 1. Okay, well, cosine of pi over 2 would give me 0. And pi over 2 minus pi over 2 would give me 0. Well, 0 divided by 0 is indeterminate. And again, you can either write it out the way I wrote it here, or you can draw arrows to clearly indicate that you have 0 over 0, which is telling me that we have L'Hopital's rule. So what do? It's still limit as x approaches pi over 2. The derivative of negative cosine, just like what we did up here, would be positive sine. And the derivative of x would be 1. Well, now when I plug in, sine of pi over 2 is 1. And 1 divided by 1 will give me 1. That's our answer. So as we move forward, plugging in 0 here, 7 times 0 is 0, minus 0 is 0. Because remember, sine of 0, I'll just write it right here, is 0 pair 1, 0. And then down here, you also get 0. 0 squared, and then sine of 0 is still 0. So what do we have? 0 over 0, that's L'Hopital. And we take the derivative of the top and the bottom. So the limit as x approaches 0 of 7 minus cosine of x over 2x plus. Now this is the chain rule. The derivative of sine is cosine. You leave 3x alone, but then the derivative of 3. So now we can actually plug in direct substitution. Cosine of 0 is 1, so 7 minus 1 on top. 2 times 0 is still 0. Cosine of 0 is still 1, and 3 times 1 will give me 3. And I guess 3 plus 0 is still 3. And 6 divided by 3, you get an answer of 2. Now, embedded within these problems could potentially be another, like doing the product rule or doing the quotient rule. Okay, because as I look at this, if you were to do the top, we'd have plugging in 0, 0 times 1, which is still 0, and in the bottom you have 0 plus 0, which is still 0. 0 over 0, L'Hopital's. Let's keep going. Now in the top, that's what I'm talking about, is we have the product rule when we're doing the derivative of the top. Derivative of sine is cosine. You leave cosine alone, so it becomes cosine squared. Now I would put plus, except you leave sine alone, and the derivative of cosine is negative sine. So that's where that's coming from. The derivative of x is 1. The derivative of sine would be cosine. You'll leave 2x alone, but it is the chain rule, so bring that 2 in front. And now when I plug that in, cosine of 0 is 1, squared is 1, sine of 0 is 0, squared is still 0. 1 plus cosine of 0 is 1, times 2 would be 2, plus that 1 would be 3. And sometimes we need to do multiple L'Hopital's rule, which is okay. We can do that. Because if we plugged in cosine of 0, we'd get 1, 2 times 1. I guess I shouldn't draw it out. You would get 2 minus 2 times 1 again would be 2. So we do get 0 on top. And bottom you get 1 minus cosine of 0 is still 1. You get 0 on bottom. 0 over 0, that's L'Hopital's. Okay. So the derivative of the top, x approaches 0. We would get negative 2 sine of x. And then that would be minus, no, turn that into a plus, or sine of 2x over derivative of 1 is 0, derivative of negative cosine would make that positive sine. But I think it's pretty evident that in top you get 0 again. Sine of 0 is 0, sine of 0 is 0, 0 plus 0, and 0 on bottom. So you just do L'Hopital's again. So the derivative of negative sine is negative cosine, and plus becomes 8 cosine of 2x over cosine of x. And now we can get an answer. We end up with negative 2 plus 8 over 1, which would give me 6. I'm just going to double check with my answer key. You know how confident I am. 1, 2, 1/3, and 6, which is exactly what I came up with. All right, I'll see you in the next video.